have like at least an hour break between 5 and 6 weeks. So this problem's got, let's see. Oh yeah, no problem. But I don't know how you would know how to do this if you didn't like know like this. Like if you didn't have physics class. Okay. So each, yeah, but like, so the tension here, I feel like it's not intuitive to know that like the only component actually not that is the weight is like the vertical component. Yeah, that's not. I like it. Yeah, that wasn't physics. Totally. But physics is applied mathematics. That's all it is. Physics is math. You could walk on, touch, look at, throw around. So math is math. But yeah, if you've taken any physics, it should look very familiar. You start thinking free body diagrams. You start thinking everything becomes a point. Crush everything down. So they want to know what the weight is. Right? What's the weight of the chain? So I don't know. Where would you draw the weight? What direction is the weight acting at? Straight down. Straight down. You got weight. So, why is there tension in this system? Why is there tension? Because if there wasn't, what would happen? What does the tension accomplish? So if you're holding, can you imagine holding up a heavy, you got a string on the bottom, is this kind of heavy little thing, you're holding it, and there's tension. What happens to the tension if you let go? Disappears. And of course, what then happens? The weight plummets. I love it. So if suddenly the tension were gone, you know, Indiana Jones, no, all right. You know, starts to fall towards the alligators or the crocodiles, whatever version species they were. Oh, all right, you guys semi with me here. So, what does the tension accomplish here? The weight wants the bridge to fall down. That's the weight's job. The tension's job is to keep it up. So, what is the tension supposed to do to the weight? It's supposed to counteract it. I love it. You even said the word I was thinking. I love it. You guys with me? Yeah. Now, what component of the tension is accomplishing that? The Y. The Y component, right? This component's not really doing much anything. You kind of with me? A little bit? This component, whatever that is, I'm going to call it T1. What's got to be true then about these two?
They're parallel.
I like it. They're parallel by definition.
Equal.
It's not really going out on a limb.
Equal.
They're equal because the angles are equal. I like that.
All the same direction.
Same direction? And maybe how does it relate to the question? These two tensions together have to equal to the weight. So all the forces acting in the same or opposite directions, right? In the Y direction or the X direction, they all have to be equal if I have a system in equilibrium. You don't have to know physics to know this, right? You have to lift on something at the same weight it is in order for it to stay there. If you lift on it heavy with more force than it weighs, it's going to move upwards. With less force, you're not going to move it. You're not going to move it up. All right, that kind of makes sense. So now it's just a matter of breaking this down. What is T1 going to be? You got the angle. You want this side of it. Screw it. That's all I'm going to do. You got a little triangle. You can put that together. You guys see how to attack this? You should. This is not a difficult problem. Believe it or not. I know what T1 is. Don't I? Where's T1 in this triangle? It's here. Yeah. And this is... Alright, so now we're back to pre-calculus, or trigonometry. I like it. Which a lot of vectors will feel like you're back in trigonometry class, and it should, because vectors are all about direction and magnitude. That's trigonometry, really. So this should feel like old school stuff. You just freak out because you're expecting the new school stuff to, finally get sprinkled in there. All right, enough of that. Is that decent enough to get started on that? So it's nowhere near as hard as it sounds at first. Bless you. There's no way to know when that's true and when it actually is as hard as it sounds. I'm sorry. I just can't tell you how to do that. Anything else from homework stuff? We haven't quite finished 12.3, so if you started doing stuff with projections and components and all that stuff, we haven't talked about that yet. We got to finish that up. All right. I'm an optimistic fool. Yes? 46? Okay. So what's happening with 46 on Thursday? I am going to bring the solution. Yes. Because it's a hard problem. But I want to let you just try it out. Don't devote a lot of time to it, but don't devote no time to it. Do something with it, right?
You said 46.
Yeah. The infamous problem. If that's the only problem you haven't got done, go ahead and turn in section 12.1. Shit, let me look at it. I'm not going to make you do it over again. I'm going to give you the answer to 46, but I want you to try something. Good. Look at that. Bam. Sweet. Look at that. I get my power from your homework. Weird demon. Oh, Christian.
Yes.
Can you put your name on there for me, man?
I do run the power from your unhappiness.
I drink your tears. All right, that's enough of that creepiness. We'll get back to the math creepiness. Thank you. Cool. All right, anything else?
You take it close to us, right?
What's up? Let's not. You can turn it in at the end.
Okay.
I don't want to bibble stamp you. You know, when you come in, just turn it in. Or on the way out. One of the two. Cool.
You're taking close to us, right?
I'm taking whatever the hell you got. Show me what you got. Yes.
Just to clarify, the homework all needs to be in before the test.
By the day of the test. You can still turn it in after that, it's just late. If you turn it into the next day, it's not going to kill you. The later it is, and the more you have late, the worse it will be for you. I like it. All right. And just to remind you guys, I think we had this discussion about how you should make homework work for you. Don't finish sections and then not even do anything from subsections because you ran out of time. No, you're getting close to the depth, and then you go to the next section, do something. You go to the next section, you do something. You turn in what you've done. I'll say, what the hell? And you're like, dude. You finish it when you can. It's a great conversation. What the hell? Dude. All-purpose word. Dude. Yeah. Yeah, exactly. That's a whole conversation. Dude. There you go. Oscar, right there. Okay. Anything else from homework? Got an ocean of you not asking anything, which is okay, as long as it's going okay. Okay. So let's get back into where we left off. We talked about dot product. And I really want to make this clear because dot product and cross product are so stupid important. I really want to make sense. We defined dot product. I don't know if you guys remember how I kind of defined dot product. I did that example. It was kind of a weird example where I was paying you so much money for moving a box so far. It's a little weird because I wanted something you can physically relate to that incorporated the angle. And that's really the best example I could come up with. But that's where we started, and then I kind of proved why it relates another way. So what two ways do we have to calculate a dot product? Let's say these are in R3. What does this mean, by the way? If you've been reading the book, hopefully you know what that means.
Three-dimensional.
3 dimensions, XYZ, I love it. So what's one way to calculate the dot product?
So A1 times B1 plus A2 times B2 plus A3 times B2.
All right, there's one way, right? And that's not the first way we came up with, but eventually we proved that it equals this. I don't know if you were there for that.
Isn't the one with vector A plus vector B?
Yes. So the other way to do it is
Absolute vector A
good. The length of vector A,
times the absolute length of vector B
length of vector B,
times cosine B.
cosine. You good? Okay.
I had a question about those. So, are those are interchangeable? Like, or do they come out to the same thing?
Oh, so do you mean A dot B versus B dot A?
No,
Or-
because I think I'm getting.
Oh yeah, these would come out to the same exact number. They have to, because they
Right, so-
both represent this.
So that top line AB is the absolute value of AB in the second one.
So this number will be the exact same as that number. Which, if you weren't here
Okay,
last
I get
time, it doesn't make any damn sense at all, just on site. Why would this have to equal this? Well, there's a lot of freaking steps in the middle to show it, right? So that's the bad part of math, is if you forget the derivation, you start to lose faith in the math, because there's no way you can just look at it and go, well, yeah, of course. Because it took me a while. I don't know if whoever was, I think most of you guys were here. It didn't take us a little while to get to there. But we got there. So we proved it. Now we can always use this. And what's the immediate thing I use this for? Almost impossible to do this thing in 3 dimensions. It's really not easy in 2 dimensions. Finding the angle between 2 vectors. Right? And in fact, I could draw 3D sort of, but this will work in 80D, right? It'll work in 1,000,000 dimensions. All right, just take a look for it. It just will take a little while to write that out. All right, how we doing? There's one chair up here in the crane your neck seats up here, late to the movie. All right, so that's what we sort of did last time. And the immediate consequence was, how would I get the angle? I would just do the dot product this way, right? Divided by the lengths. And then what do I do with that?
Inverse cosine.
Inverse cosine. I like it. Yes. All right, so let me ask you this question that'll kind of relate to this. If you've been reading the book, they talk about direction cosines, which gets interesting. And they're not even that big of a deal. But who remembers in R3, who can tell me what this is in R3?
Unit vector along the x-axis.
Cool. And is it in component form?
1, 0, 0.
I like it. How are we doing there? Is that cool? And of course, J hat would be 0 and 0 and blah blah. I like it. Put them all together, they look like an identity matrix. Matrices come into play, holy shit, later. So if I had this vector here, gather B, what would this be?
A1, 0.
Just A1. I like it. Cool. So, all right, let me stop there for a second. Does that make sense? Is that cool? So dotting a vector with I, J, or K really just pulls out its component in that direction. Let me just stop there. You guys understand? The dot product is all about, in a way, the amount of this vector that lies in the same direction as another vector. But if they're not unit vectors, they kind of multiply their magnitudes too. So we've got to kind of account for that eventually. Here, this is a unit vector that I'm dotting it with, so it actually just pulls out. So, of course, A dot J would be A2. Amazing. All right, so if I wanted to figure out, using this procedure here, if I wanted to figure out the cosine of the angle between a vector and the x-axis. All right, let me let you absorb what I'm talking about. This will be nice. It should be nice because the vector that I'm dotting it with is going to be a unit vector. That's awesome. And we don't call this theta. We specifically call it alpha. So between the vector and the y-axis would probably be the angle we would call it. This is alpha for the x-axis, probably beta for the y-axis, and then probably
Gamma.
gamma for the z-axis. So I'm going to call this cosine alpha. I'm kind of working with this.
A1.
Stay with me now. Yeah, exactly. So let me write it out. It'll be a dot I, because that's in the x-axis direction, over the length of A. And what's the length of I? It's a unit vector. The length of I is 1. So this is a specific example of this process. But you can see how it's remarkably useful. It tells you, it breaks a vector down into the angles between all of the primary axes, right? The x, y, z axis. That's a really good thing to be able to do. All right, let me let that sink in for a second. No. Is everybody cool with this process here? Speak up if you're not, because if you're not, there's at least 8 other people that aren't either. All right.
I'll just raise my hand.
Yes, okay. So we're all cool with this being a definition of dot product, and so is this.
Yes.
So equating these allows me to get here.
Yes.
So I could find the angle between any 2 given vectors in any dimensions.
Sure.
Kick ass. That's pretty impressive, right? List that as a skill on LinkedIn. This, please let this be almost silly. This is just saying, well, let me make one of those vectors x, y, or z unit vector. That's all. This is for any vector anywhere and doing whatever. This, what I'm talking about right now, is more specifically about the x-axis. A vector with the x-axis, right? All right. So this will be the cosine, the direction cosine. And so just finishing this out, where am I at? I think I got everything out there. Good. And of course, somebody told me, what's a dot I?
A1.
A1. So what would cosine beta be? Can you follow the logic? Beta, of course, was the angle between the vector and the
Y-axis.
y-axis. Cool. Alpha is the angle between the vector and the x-axis. All right. So I can have some vector in 3-dimensional space. Oh, shit. Pop! It's vector A. And I want to know, all right, what's the angle that makes with the x-axis? What's the angle? Well, that's the y-axis. What's the angle that makes with the x-axis? What's the angle that makes with the y-axis? What's the angle that makes with the z-axis? The cosines of those, really. That's all this is. That's it. And you're like, well, that's quite a bit, Jeff. But if you understand this, you have to understand this. This is just a very specific application of this. So cosine beta would be what? A dot J, which will be A2, over the length of A, so forth. I like it. So that'll show up when they're asking for direction cosines. That implies, that by definition means that you're comparing a vector with each of the unit vectors in the x, y, z direction. The I, J, K vectors. You're welcome. Got convert up here. I like it. Believe in the direction cosines. Okay. So they discussed this on page 850. I like it. So let's try one. Let me let you guys try one. Find the direction cosines for this vector. Look at that. That's yummy. Yeah, I don't think you know what yummy means, Jeff. Is that a strange way? This is where you can talk with other people near you. If they look like they might know what they're doing. You can draw a duck. I won't know. I'll just go, oh, you're trying this. Good. I know now somebody's probably drawing a duck. Extra credit if it's Howard did it. Are you Julian? Julian, where's Julian? Julian. I replied to your email. I got to remember to talk about it. I was having trouble with the Blackboard account, so it got fixed. So now I've got the NetTutor up there. You're asking about that, right? Okay. Thank you.
So you take the magnitude.
So,
All right. And yes, you do need to know this because you need to know this. You just need to know this. I'm not going to let you write this down somewhere. Don't tattoo it in the back of your neck and help your friend out behind you. That's dedication, actually. I would probably be impressed. I'm not even mad. I'm just not even mad. I'm impressed. But now specifically for the x-axis, the alpha, that of course is going to be, in this case, what?
The inverse percent of 1 over.
So now for us, yeah, B, the length of B will be 1. That's crazy. Because it's for us now, for the cosine, direction cosines, they're all about ijk, so they're going to be, the one vector is going to have a length of 1. What's going to go on the top of this?
so A1. So A1. Negative 1.
So the x piece, that makes sense. So x-axis should have the x piece in there. And now I just got to know the length of A because the length of B is 1.
Square root 14.
Yeah, let me get out of there. So when you do this, you get square root of 14? Yeah, 9, 10, 14. Yay! So that's the direction cosine. I'm sorry.
Yeah, what's B?
Oh! For the x-axis, B will be I hat, right? Is that, I mean, that's it.
I think so.
In general, it could be any damn vector. It can be any two vectors I want. If I'm talking about direction cosines, I want to know, sort of like, what's the angle between the vector and the x-axis, the vector and the y-axis, the vector and the z-axis, right? Those three things. So for the x-axis, I pluck off the x component, divided by the length, right? And the length of B will be 1 here always, because it's going to be the unit vector, by definition. All right, so this is just a specific application of a general process. That's it. So if you understand this, you have to understand this. All right? In fact, people that think you have to memorize everything, no. You just memorize this, and then just put the specific shit in for something like this. Okay. Just because. What alpha in whatever units you want?
105 degrees.
105 degrees? Cool. I like it. And then, so what would, for the y-axis, now B would be j hat cosine beta.
2.
Yeah. 2 over the square root of 14?
58.
Okay. About 58 degrees. For beta, sorry. Let me not do that. Beta is approximately. All right, let me stop there for a second. I knew that none of these angles would come out to be 0 degrees because
They're not.
this vector is not lying on any axis, right? It's a combination of all three axes. It's somewhere between them all, so that, you know, that at least that makes sense. And then for the z-axis, B is k hat. Real quick, what does I hat mean?
It's a vector of 1.
All right, it's a vector of length 1.
Pointed in the positive direction, the x-axis.
Yes, pointed in the positive axis direction. I love it. I just took your words and moved them around. That's plagiarism. I love it. That's like not lazy plagiarism. At least they moved around. Cosine gamma. Oh shit. Equals Negative 3 over rad 14, so then gamma is roughly
143.
143. Sure, why not? And again, what's really nice about inverse cosines as related to inverse sines?
Don't have to worry about reference angles.
Don't have to worry about reference angles. Inverse cosine's output is 0 to 180. It'll be the true angle. That's crazy. That's beautiful. You gotta love it. And maybe. So right now, if you understand this, you're golden. If you don't understand this yet, you're making too much of it. You really are. Yeah.
The thing that you showed a second, is that underneath that? That's
Here?
the same thing as that?
Exactly. This is the idea behind what we did over there. If the B I was using was I hat, then A dot I hat would just be the first piece. And the length of B would be 1, because it's the unit vector in the direction of the x-axis. That's what I hat is. Right? It's not a new Apple product. Sorry. The I hat. In statistics, we have a P hat, and I always say that's the thing you don't want to wear. Here we have I hat, which sounds better, but still. All right. All right, so that's an immediate other use for this. It's really the same use we used already, just given a different word. Direction cosines, same stuff. Okay. So now let's get into this slightly freakier stuff, projections and components.
What's that term? Is this 12.2? Yeah, or 12.2.
12.3. Before I do this, let's do a little quick thing about dot product. Can you find A dot B? Just take a second. I'll make sure people at least remember this. Don't say anything out loud. At this point, you should know how to do this. The math here is too nice to believe. You're like, are you sure this is Calc 3? Yes.
Okay.
Okay. Should be all the time you need. So what is A dot B? Yeah, it'll be 5 times 0 plus negative 2 times 5 plus 3 times negative 7. Get out of there. So that is negative 31. Sweet. I love it. Good point. So the dot product is a scalar idea of multiplication of two factors. Why did we define this thing this way? Because it's incredibly useful, right? I like it. Why did we define 2 times 7 to be 14? Because that's remarkably useful. We could have defined it other ways, believe it or not, but we didn't. All right. Okay, cool. So let that be simple. Would it change any if I did this?
Add more.
The answer would be the same, right? Because you would get 0 plus 0 plus 0. So again, I just want you to really, we're going to focus on like 2 and 3 dimensions, we are, but this work we're doing works in any dimensions, even though you can't picture it. Try to picture 6 dimensions. Watch your brain slowly fry itself. Don't do that, it'll freak me out. You're in the corner going, 6 dimensions, he's going for 6. Sorry. Alright. He's gone past 5. Let's see how far you can make it. Alright. Alright, so projections are exactly what they sound like. I think this book, does it do this backwards? Sort of? No. I like it. So to kind of work our way up to projection. So what a projection is going to be, and we'll do this step by step so I can really show you what the two things mean. This idea is almost too good to believe. Let's make this the easiest case to look at for first. By the way, how many dimensions do those vectors exist in? I like it. Infinite number. I can restrict it to being a two-dimensional problem because I have a plane well defined. Any two vectors define a plane. But like, how many dimensions is that point? How many dimensions is that point in right there? 1, 2. There's a lot of 2s. 3-dimensional space. 4, 5, 6. An infinite number, right? What's my point with that? We can work a problem out in a certain dimension, realizing that it exists inside of a larger dimension. I don't know if that's going to help or whatever. What else is good? That's like the way it sounded. So now watch this. I want this to be clear as to what the wording means. So the projection, how do you read this? Well, which vector would you say is on the other one, is on top of the other one? B is on top of A, right? So this is a projection of B on A. So this is a projection. This is one thing to really get down. B on A. And this is the projection of, no, Jeff. There you go, buddy. A on B. Blah, blah, blah. Let's look at this one first, because I got it drawn so that it's easy to look at this. Let me stop there for a second. Anytime you learn a new symbol, you got to take a second and understand, are you reading it correctly?